In the previous video or 2 videos ago, we talked about the idea of a moment of a force, a moment or torque. That means the same thing. And what we talked about was that, so in engineering mechanics, we're analyzing the effects of forces on bodies, whether it be the motion that they cause, or if there's no motion, then how they're resisting that motion, like the supporting forces that resist the motion. And we talked about how there's certain situations where just having forces is not enough to describe the entire situation or the entire effect of the forces. So, for example, we have this force F being applied to the wrench. But what if we had another situation where we applied this same force here? Well, we know intuitively that these are 2 separate scenarios, at least for the case of this problem here. Yes, this is the same force, but this situation is going to cause more of a rotation of this bolt than this force. So to proceed forward in engineering mechanics, we need to have some measure of a tendency of a force to cause rotation. And that's what a moment is. That's what the moment of a force is, either moment or torque. Okay, so we're going to need to define something, define this measure. This definition is made by humans. We can pick this definition of the moment or the tendency of a force to cause rotation to be whatever we want. Well, the first thing to note is that it's not enough to say that a moment of a force is the tendency of the force to cause rotation. We need to be more specific. Rotation about what? About a point. So, more specifically, the moment of a force is the tendency of a force to cause rotation about a point. What point? Well, you choose the point. Whatever point you pick, based on the nature of the problem, right? Because if we choose this point for this problem, well, then all of a sudden, this situation, this force has a greater tendency to cause rotation about this point than this force. So the moment depends on the point you pick. Okay, so now, intuitively, what's the best way you would think to define this, a moment of a force, the tendency of this force to cause rotation about a point? Well, we think about a wrench. It's like if we said the magnitude of this force times this distance here from the point. And it's not just a distance, it's like that perpendicular distance, right? It's perpendicular to the line of action of the force. Because if you look here, the force is being applied at an angle. Well, now we don't want to say F times D times this D. It's more of, it's F times this D, this D prime here, right? That's that perpendicular distance from the force to the point. And that's exactly what a moment is. It's the magnitude of the force times the perpendicular distance from the force to the point. That perpendicular distance we call the moment arm. So in this scenario, if we erase this, okay, so in this scenario, D is the moment arm. In this scenario, D prime is the moment arm. In this scenario, the point is along the line of action of the force. There is no moment arm here. This is causing no rotation of the bolt. There is a force here, but it's the same force, F, but it's causing no rotation of that bolt. And the reason is because the moment arm is 0. Okay, now it's important to note that any force, any of these 3 forces here, or any force that's ever existed in the universe, there's an infinite number of moments of that force. Why? Because there's an infinite number of points either on the line of action of the force or away from the line of action of the force, right? I could calculate the moment of this force about this point. So this force has a moment about this point. But this point is not, that moment is not relevant to this problem here, right? So that's why in some situations you talk about, well, this force has no moment. This force doesn't have a moment in the context of this particular application here. Okay, so what we're going to do now is you can see how in some circumstances you'll have a force you're dealing with, and you want to be able to say, okay, I need to analyze what the moment of this force is about this point. So in general, What is the absolute most general way to calculate the moment of a force about a point to where it satisfies what we just talked about, where it has that you're multiplying the magnitude of the force times the perpendicular distance from the force line of action to the point? Okay, we're going to first talk about here the most general method to do this. This applies in 2D, 3D, in any situation. So we're going to use vectors to do this. But remember, in 2D, if you wanted to, you could resolve all of your forces and your positions into vectors and use this definition. And it would be that would work perfectly fine. But it's not common practice to do that in 2D, and we're going to talk about that. But this is the general definition for the moment of a force for any circumstance. You have your force vector in space. You have your point of interest. You draw a position vector from the point of interest to anywhere along the line of action of the force. Now here it goes to the tail, but it can be literally anywhere along the line of action of the force. So the position vector could be here, it could be here, it could be here. You pick any position vector you want from the point of interest to the line of action of the force. You take R cross F, and that's the moment of the force about that point. Again, you could do this in 2D. This works for any scenario. This is completely general. This is the definition of the moment of a force. Now, okay, the cross product is a vector product. You get a vector. What you get out of the cross product is a vector. So all moments are vectors. All moments. If you have a moment, you're talking about a vector. Why does a moment have to be a vector? Well, the reason is because the direction of the moment vector, that's the axis of rotation. But how many different possible axes of rotations are there? There's infinite. Any vector in 3D space can be a moment axis. So the magnitude of the vector, the length of the vector, the magnitude of the vector, that's like the intensity of the tendency to cause rotation. And what's that a function of? What's the magnitude of the moment vector a function of? How large the force is and how long that moment arm is, right? The longer the moment arm, the bigger the magnitude of the vector. The larger the force, the bigger the magnitude of the vector. But then also you need that direction. What's the rotation axis? Okay? Now you might be saying, well, wait a minute. So don't we need to, we can pick any position vector we want that goes to the line of action of the force. But don't we need to make sure that that position vector is perpendicular to the line of action of the force? No, because the cross product's going to take care of all the perpendicular stuff for you, right? The cross product is R, magnitude of R, magnitude of F times sine of the angle between the vectors. That sine of the angle is what gives you that perpendicular component. That sine of the angle is what makes it takes the component of the R that's perpendicular to the line of action of F. Now, we want to be perpendicular to the line of action of F, but we also want to be you can think about it perpendicular to the point O as well. You can't really be perpendicular to a point, but right, you want that pure perpendicular moment arm. That's what the cross product does for you, right? The nature of the cross product is the resulting vector that you get is going to be perpendicular to the plane that contains R, the moment arm, and the force vector. So that's how you get, that's why your moment arm is perpendicular to both the moment axis and the line of action of the force. That's perfect, right? That's the exact definition that we want. The magnitude of F times that pure perpendicular distance to our point of interest. Perpendicular in the sense that, so you can't be perpendicular to a point, but perpendicular in the sense that the rotation axis is the line that's perpendicular to the plane containing R and F, right? That's exactly intuitively what you would think about as the tendency of a force to cause rotation. So this is the perfect definition. Okay, now what about the sense of rotation, right? Do you have to draw this curled arrow, is that part of a moment vector? This is just here for graphical illustration. You can put this curled arrow if you want. But if you see a moment vector, you don't need that curled arrow. The moment vector, just as it is, tells you the sense of rotation from the right-hand rule. So if we came to this moment vector, if we saw this moment vector, we would put our right hand, the palm of our right hand, along the direction of this vector with the thumb along the head of the arrow. The curl of the fingers is the direction of rotation. Okay, now how do you know, but how do you, whenever you're calculating this, how do you know whether or not to put this vector here or here? Well, that's with the definition of the cross product. If we come here, you cross R with F. So you could just visually bring the tails of R and F together and then push with your right hand R to F, and your thumb is in the direction of the resulting vector. Or you can imagine like visually sliding R up, and this is the angle between the vectors, and then you push R to F here. Okay, but once you've calculated the moment vector, okay, once you have your moment vector, you can move R visually to F, and you get the moment vector. But once you have the moment vector, you put its tail at the point. A moment vector is a fixed vector. Okay, remember this. A moment vector is a fixed vector where the tail is fixed at the point of interest. Okay, now what does that mean? It's a fixed vector. So what if it wasn't fixed? How could something be a sliding vector, or how can something be a free vector? This could be a sliding vector. A moment vector could be a sliding vector if I said, okay, let me pick this as my point. Now I'm going to calculate the moment of force F about this point, right? Pick any point along the line of action of this axis. Okay, and now so I did, these don't imagine these don't intersect, right? This kind of comes over the top of this vector. So I did this, or this as an R. And if I did R cross F in that situation, and I got the exact same moment vector, so both magnitude and direction, and if that would happen for any point that I choose along this axis, then the moment vector would be a sliding vector. It's sliding because when you move it, it doesn't change the vector. It doesn't change the overall effect on the body. And so like for this scenario, we call F, as far as like when you're talking about the moment of a force about a point, the force is a sliding vector in that context, because you can move the force anywhere along its line of action, and R cross F is the exact same. It doesn't change no matter where F is along its line of action, the moment of F about the same point is the exact same. Like, you know what I mean? Like if F was here, it's not like, well, okay, you have the same magnitude of moment, but the position of the moment changes. No, the moment is always, the tail is at that point. Now, this is just for this specific circumstance, this context. But we're going to see there's most scenarios in statics, forces act as sliding vectors. But in some circumstances, they don't. But in a lot of situations, in most situations, forces are sliding vectors. Okay, now this is a little confusing because we're going to talk about later in this chapter when like couple moments are not fixed vectors. Those are free vectors. And then when we do equivalent force systems, we can like take a force and convert it into, move that force to a point and put a couple moment at that point, and that's an equivalent force system. That couple moment is a free vector. So that's a little confusing. If I just use the word moment of a force, that's a fixed vector. Because when you say moment of a force, you need to be more specific and say moment about a point. If I say couple moment, that's a free vector. That's a different type of moment. And then also we're going to see that the moment of a force about just an axis, just a general axis, that's a sliding vector. We'll talk about that later in this video, but in general, the moment of a force, you're talking about the moment of a force about a point, That's like the general definition of a moment. That's a fixed vector. The tail of the moment vector is fixed at the point of interest. Okay, now if we use the determinant definition of the cross product and fill out the determinant matrix with the components of the force and the components of the position vector, and we expand all of that out, this is what we get. So this is going to give you more of an intuitive sense of what R cross F is. So like, okay, the moment about point O, you have the component of the moment in the X direction, the I hat. That's the tendency of the force to cause rotation about the X axis. Okay, now if we look at this from the perspective of the components of F, how does this work? Because that's one thing you can do. You can take a force, resolve it into components like X, Y, and Z components or whatever, and then take the moments about the point for each one of the components and just add those up to get like a net resultant moment of the whole force. You can do that, no problem. That's what we do in 2D, right? So again, you have this F here. You can separate it into components Fx, Fy, Fz, and then find the moment of Fx about O, of Fy about O, of Fz about O, and sum those moments up. Do a vector sum on those moments, and that's the same thing as just doing R cross F. We don't do that in 3D because that's way too confusing, but we do that in 2D. We'll talk about that. But the I hat component of the moment, of the resultant moment vector, that's the tendency of the force to cause rotation about the X axis. RYFZ minus RZFY, what does that mean? Okay, so here's FZ, and then here's RY, right? FZ is rotating it like this in the positive direction. That's why RYFZ is positive. If you put your right hand along the X axis, the thumb with the thumb along the positive direction of the X axis, that's this. That's the positive rotation about the X axis. That's what, if FZ times RY, that's the rotation that's causing about the X axis. Okay, minus RZFY. Okay, so RZ is this. That's the moment arm about the X axis, Fy. That's causing a negative rotation. That's why this is negative. And then Fx is not causing any rotation about the X axis. And we're going to see the reason is because when you're talking about forces, the idea of a force causing a rotation about an axis, not a point, but if you're just talking about an axis, if the line of action of the force is parallel to the axis, then there's no moment. Or if the line of action of the force intersects the axis, there's no moment. Okay, so what you get is you get a moment vector about the x-axis, a moment vector about the y-axis, and a moment vector about the z-axis. All the tails are all at the origin. You do a vector sum on those, that's what this is, and you get the resultant moment vector. Okay, now, if you have a system of forces on a body, you can calculate a net resultant moment vector about a point due to all of those forces. You just do R1 cross F1 plus R2 cross F2 plus R3 cross F3. And this works because this has to be about the same point. You can't you have to be calculating the moment of all of these forces about the same point, because the resulting moment vectors are all going to have their tails at that point. So then you can do it. Then it's appropriate to where it's valid to do a vector sum, because all of the tails of the forces are at a point, the same point. That's what we talked about in particle equilibrium. All of the forces have the same. Their lines of action meet at a point, so you can slide those vectors and have their tails all at the same point and do a vector sum. We couldn't do we couldn't say, R. If this is another point A. So we can't say like R1 cross F1, and then this is R4, R plus R4 cross F2. Because this moment R4 cross F2 is fixed here, is fixed at A, whereas R1 cross F1 is fixed at O. You can't just add those. Okay, so you can find a net resultant moment of different forces when you're calculating the moment of each force about the same point. Now, you might be wondering, well, okay, so we get this net resultant moment. Do we put this moment and then remove the forces? We're going to talk more about this in later videos. You'll get a feel for how to apply moments and forces. But just to give you a general idea, no, you put this net resultant moment, but leave the forces as well. So what you have is you still have the forces, but you also have this moment here. And I know this is probably a little confusing. Don't worry about it too much right now. But like you couldn't say, okay, I'm going to have this point A. I'm also going to calculate a net resultant moment or just a moment of one of these forces about A and put a moment here. And we'll have this moment and this moment. You can't do that because that's implying like that you've got two F2s and two F3s and two F1s. You have to, you can only say, okay, based on the nature of the problem, what's the tendency of all of these forces or one of these forces or whatever to cause rotation about point O, and you get a moment. Then you could say, okay, well, let's look at this as a separate problem if it's valid to the circumstance. Okay, what if I took this off and we just looked at the tendency of these forces to cause rotation about point A? Does that affect the problem? Okay, but again, we'll get more into this, the idea of applying these moments and forces in later videos. Right now, we're just learning how to calculate a moment. Okay, now the next thing I want to talk about is, in a lot of circumstances, and particularly when you first start out in statics or engineering mechanics, you're going to be working problems in 2 dimensions in a plane. Now, as I mentioned, you could absolutely use the vector, the R cross F, put your forces as vectors, all the position vectors as vectors, do R cross F, and you could do all your analysis with what we just talked about, and that would work fine. But that's not typically what's done. That's most likely not what you're going to do. So let's talk about what's most common for how people work with moments in 2 dimensions. But before we get into this, I want to note that I think the problem with the way we work with moments in 2 dimensions is that it makes it so easy to completely forget about the general definition of a moment, or like the general idea of what you're doing. And so what I want to do is make it clear exactly how what you're doing in 2 dimensions relates to the general definition of a moment. Okay, so here's a couple 2-dimensional cases. If we look here, so we want to calculate the moment about point O. And let's say here, they give us like the resultant force. Instead of, they don't give us the components, we have to find the components. Well, what's commonly done in 2D is you take all of your forces and you resolve them along the X and Y axis, and then just find the resultant sum of all of those forces, all of those component forces about the point of interest. So here that would be point O. And so the moment arm is easy to calculate when you have all the components. Like here's the moment arm of this 50 Newton force. This 60 Newton force has no moment arm. This 20 Newton force, this is the moment arm, right? And it's rotating it this way. The 40 Newton force is rotating it this way. And here's the moment arm, okay? And the convention is that a counterclockwise rotation about the point is positive, and a clockwise rotation is negative. And that's really it. You don't think about the idea of a vector. It's just like either a positive or a negative rotation. Okay, but when you think about more of the official definition of the moment, what you're doing is, so like if we took R cross F, of this force here, so we drew a position vector from O to here, and then we got it as a vector with I and J components, and then we got this force as a vector with I and J components, right? There's no Z components. What that's giving you is, if we extend the line of action of this force, the R cross F is it's the magnitude of this force times this distance here. This is the moment arm, okay? And if we wanted to calculate, if we wanted to do like a scalar analysis and not use the cross product, and we wanted to just go ahead and extend the line of action of this force and then use geometry and find this D, we could do it ourselves. We could say F times D, and like you can do that. But it's more common practice just to break the force down into components and sum all the moments of the components. But you could do the magnitude of this force times this D, and you could do that manually, and that's the result. And you know, this is more intuitive in my opinion about what the moment is. Like it's the entire force times that perpendicular distance to the point. Now, why is it so much easier? Like in 3D, it's hard to just do like F and to find that perpendicular distance. The reason why is because in 2D, the moment at the axis of rotation is always into and out of the page. So like any line we draw from the line of action of our force is automatically going to be perpendicular to the moment axis. We don't have to think about, well, R cross F, what's the perpendicular direction of R and F? That's already set for us in 2D, right? This is going to be perpendicular to the moment axis. Okay, and then, but again, it's easy to forget, even when we're working in 2D, you're getting a vector though. You're getting a vector that's directed along the Z direction, either into or out of the page. And the reason why counterclockwise is positive, because if you put your right hand along the positive Z axis, well, so like the thumb is in the direction of the positive out of the page, the curl of the fingers is counterclockwise. Okay, now if we look here, this is a planar problem. And so if we look here, you can calculate the actual moment arm in the plane, the perpendicular distance, it's perpendicular to the line of action of the force, and do F times D. But more commonly, you're just going to resolve this force into components. And then say, okay, this component times D, and then this component doesn't have a moment about O. Now, just to point out, we mentioned in the vectors in space video when we talked about the cross product, I think we talked about this. We definitely talked about this for the dot product, but the dot product has that duality, right? Like, so, and so does the cross product. So the cross product is the magnitude of, or the cross product in this situation is the magnitude of R times the magnitude of F times sine of the angle between the vectors. You can look at that as the magnitude of F times the magnitude of R sine theta. So it's taking the R and turning it into the moment arm. Or you can look at it as the magnitude of R times the magnitude of F sine theta. And that's kind of what it's doing in that circumstance. It's saying F sine theta. It's getting the component and leaving that original distance the same. In other words, here, for this scenario, if we did R cross F here, you can look at it like it's what it's doing in the background is it's taking the magnitude of F time, and it's finding that sine of theta is finding the moment arm, right? It's turning this, like the theta is somewhere in this triangle, and you're getting this component with the sine of theta, the D, or it's breaking it down, the force down into the corresponding components that way. Like you see, or like you can look at it as the R times F sine theta, which would be like you've got, it's finding there's a component of this force that's parallel to this line. It's taking that out. It's finding the component that's not parallel to this line, and then multiplying that times this distance. Okay, so just here's another illustration of that perpendicular moment arm distance, right? That's how you can view it in 2D if you want, or you can just break these down into components and sum the moments of 6 different components of these 3 vectors in total, or you can just find the perpendicular moment arm distance and do F1 times D1 plus F2 times D2 plus F3 times D3. Okay, now the last thing I want to talk about is the moment of a force about an axis, about a specified axis. And I touched on this earlier in the video, but we're going to get into it more specifically now. So here, if you want to find the tendency of this force to rotate the bolt or the lug nut here, okay? So you do R cross F, right? So R cross F coming perpendicular to the plane containing R and F is this moment axis. Okay, but that's not what you're looking for, right? You want to find the moment of this force about this axis, right? So how do you do that? We can look at another example here. You've got this force. You want to find the moment of this force about this axis, right? Because it's constrained to rotate by these joints here, just along that axis. So what's the moment of this force about, not a point, but about this axis? How do we do that? Well, okay. First, from a scalar standpoint, so if you're not going to use the R cross F definition, the vector formulation, what you're doing is you're finding the perpendicular distance between the axis and the line of action of the force. That distance is perpendicular to both the axis and the force line of action. It has to be perpendicular to both. If you find that distance, multiply the force times that distance, that's the moment about the axis. So if you want to do it just from a non-vector standpoint, you can do it that way. You see how this is perpendicular to the axis and to the force line of action. Okay, and then I mentioned this before. Note that if the force line of action is parallel to the axis, the moment of the force about the axis is 0. If the force line of action intersects the axis of interest, the moment of the force about the axis is 0. Okay, so you see here they're not parallel and they don't intersect. Now, okay, now if it's more complicated and you want to do it using vectors, what you do is you pick any point along the axis of interest, right? And you can do that. You know the axis. You're specifying the axis. Pick any point you want. Find R cross F about that point. Now you might be saying, well, wait a minute. I thought that isn't the moment vector going to be different depending on the point you pick? Right? Because that's why we said moment vectors aren't sliding vectors. Yes, it will. It will. But okay, but still you do that. Then you dot the moment vector that the R cross F of any point on the axis, you dot that with a unit vector in the direction of the axis. And we talked about in vectors in space, what you're doing here, that's how you find the component of a vector along any direction. And so that's the magnitude of the moment of the force about on that axis. If you want that as a vector, then you just multiply it times, you do unit vector in the direction of the axis dotted with R cross F, and then you multiply that times the unit vector again to turn it into a vector. And if that's confusing to you, if what I just said is confusing to you, go watch the vectors in space video or the cross or the, was it the, go watch the vectors in space video and then go fast forward if you need to the, where we talk about the dot product and cross product. When we talk about getting the components of a vector along any direction using the dot product, or getting a vector in any direction, a component vector in any direction. Okay, but what you can see is that no matter what point you pick, it doesn't matter. You're going to be getting the same vector, the same resultant vector, no matter what point you pick. Because yes, R cross F is different depending on the point that you pick, but but at the end of the day, you're just finding the moment of that force about the axis. So like you might have a vector depending on the point you pick that has a larger magnitude, but then its angle relative to that axis is going to be a little bit larger. So the dot product's going to it's like the projection's going to end up being the same no matter what. And that's why if you're just strictly talking about a moment vector about an axis, that's a sliding vector. And I know that's kind of confusing because you think, well, isn't like a general moment vector then? You can slide, well, why can't you slide that along the moment axis? Because that's a different context. That we're talking about the moment of a force about a point. That's changing. We're in this context, we're talking about the moment of a force about an axis. So no matter what point you pick along that axis, you get the same moment vector. So you see how the idea of if something's a sliding vector or a fixed vector or a free vector depends on the context, depends on the problem.